Hello, today I would like to introduce limits, but I would like to try to do it in maybe a little bit different way, coming at it from a perspective further along in a calculus class than you usually do, from a perspective of derivatives. Limits and derivatives, both of those are new words to you as you are trying to learn calculus, but they are at the heart of what calculus is. My goal with this video is for you to understand the concept behind a limit and then start seeing some of that notation. And so to get there, we're going to look at this graph on the left. It is the graph of y equals 2x squared. So a pretty basic, pretty simple graph. But what if I look at this point right here? That is the point 0.5 comma 0.5. And I'm just wondering to myself, what is the slope of this equation right there at that point? It seems simple because when we think of slope, we think, oh, that's pretty easy. Because what we have always dealt with is when we have a straight line, what is the rise of a run of this? What is the slope? M equals what? However, that is with a straight line. Things change when we start dealing with curves. It gets a lot more tricky. And in fact, calculus is the very thing you need in order to find the slope or the rate of change of something that is changing. It's not continuous like a line or a linear function, but rather it's changing over time. Okay, so you say, well, then hope's not lost. I can still figure this out. And your first attempt at trying to find what the slope of this might look something like this. And I really love this type of investigation as we try and delve into trying to figure out how could I figure out the slope. And it might be that you estimate it, that you draw this line right here, which is what we call a secant line, which is just a line that crosses a graph at two different points. And you say that sort of approximates what the slope would be right here. And now to help us along, I'm going to introduce another term, which is a tangent line. A tangent line is a line that touches another function at exactly one point. This tangent line in purple would have the same slope as our point on the function. So really our problem is down to, we're trying to find the slope of that purple tangent line. And you say, yeah, if I draw that green secant line, it kind of estimates it. And I know how to find the slope of that, because guess what? It's a line. So you say, well, slope is equal to y2 minus y1 over x2 minus x1. Easy stuff. I'm rocking this calculus. This point is at 0, 0. The other point is at 0.5, 0.5. So we go 0.5 minus 0, 0.5 minus 0. That is 1/2 over 1/2, which anything over itself is just 1. So you say, all right, that's got a slope of 1. Pretty good. I'm done here. Out. Okay, yeah, but we got to get that better. So you think to yourself, how could I improve this? And you come up with the idea, well, what if I slide that point over closer to the point where my tangent line is? So now we have this new secant line. As our lines get a little cluttered. And you say, all right, let's find the slope of that. So m equals, now we're at the point 0.2, comma, our function is 2 times x squared, so our point would be 0.2 comma 0.08. So we go over to our slope and we go 0.5 minus 0.08 over 0.5 minus 0.2. Yeah, they're smaller decimals, but it's not too bad. 0.42 over 0. And we get 1.4. And you're like, yeah, that's right. I know my purple line's a little steeper. I think I'm getting a little more accurate with this. And you say, well, I can do better. What if I slide on up to 0.4? So now my new secant line is getting a little steeper and also a little closer. And this point crosses it at 0.4, comma 0.32. And so you go back to your slope formula, and you go 0.5 minus 0.32 over 0.5 minus 0.4, 0.18 divided by 0.1, and you get 1.8. And again, you're like, yeah, doing pretty good. Well, I can do better. And so what do? I think you already know by this point, but you snuggle in a little closer to that 0.5, and you say, I'm going to be pretty daring. I'm going 0.49, comma, 0.4802. And you say, now I got it. Find that slope. Got real small decimals now, but okay, because you know you're close to the solution. You get 0.0198 divided by 0.01, and that is 1.98. It seems like my slope is slowing down in how it's changing with each one. It only grew by 0.18 on that one. One more time. Okay, I can do just a little better. Let's try one more. Pull it out. You go here, 0.499, and you say, what would that be? And you plug it in your function, you get 0.498002. You go back to your basic slope formula, and you go 0.5 minus 0.498002 over the 0.5 minus 0.499. And again, we get some pretty small decimals. Divided by the 0.001. And when we do that division, 1.998. And now something's cluing in your head that I think this slope is approaching a certain value. And then it clicks, well, why not just put my second point right at 0.5? I've been getting closer and closer, but why not just get there already? I'll have my second one at 0.5. Here we go. My slope is 0.5 minus, I guess it's 0.5, because the second point is also 0.5. 0 over 0. That's why I couldn't just pick the same one. I get undefined, error. But yet it seems like as I'm getting closer to 0.5, my slope is approaching 2. And I think we can see how that slope is getting closer there. But if I land on 2, I have a problem. It's x minus x, 0.5 minus 0.5, it's divided by 0. So I have an issue. But what do I really want to do? What I want is to get as close as I can to 2 without touching it. And ladies and gentlemen, that is the concept of a limit. Kind of weird once you dive into it, but very helpful. It is this idea of getting infinitely close to something without actually touching it. Super close, but not actually touching the number. And so let me clear up this graph, and let's think about this with a little more notation and a little less numbers. Okay, so I have cleaned up the graph, and we're going to introduce a little notation. Over here, we can keep the 0.5. We'll leave some numbers in there. But what we were doing on our secant line is we were taking this point, our xy ordered pair, and we kept moving that x value closer and closer to 0.5. We went from 0, 0.2, 0.4, 0.49, 0.499. So that x value is what was moving. And at the end of all that, we said, what we want is for that x value to get very close to 0.5 but not touch it. We want it to approach the value of 0.5. And we had our slope formula, and it looked like m equals 0.5 minus the y value over 0.5 minus the x value. Okay, so that was it for each xy ordered pair. Now, what we said just a moment ago was that this x value, what do we want it to be? We want it to approach 0.5. And we want to know the value of that slope as x approaches 0.5. And so we have a little bit of notation for that. It is called the limit as x approaches 0.5 of the function you are dealing with. Now in this type of problem, it's a little more of a equation, our slope formula, but is the limit as x approaches 0.5 of your equation. How does this help us? Well, I do have an x and I have a y. Now that y we can actually deal with, because if you've had experience with math, you know that you don't really want two different variables in your equation. It makes it harder to solve. Well, we know what y equals. it equals 2x squared. And so we mess with this again. We have the limit as x approaches 0.5 of 0.5 minus 2x squared over 0.5 minus x. Now that whole notation right there of the limit as x approaches 0.5 has a lot of mathematical theory behind it. It is the concept of getting infinitely close to something without actually touching it. But you can act mathematically as if you have touched it. And after you learn some more calculus and figure out the techniques to solve this, you will find that this slope, or this limit, is in fact 2, which is the answer to our slope question. And you do that by applying different techniques of solving limits. Okay, so now I'm going to erase this plot again, and we're going to rephrase this, renotate it one more time to keep driving this point home. Okay, so I've redrawn the plot, and I did switch around where our tangent and secant lines are. It'll just help us work with the notation a little better. And this time I am going full notation, no numbers here. So this first point, we can call that our x, comma, f of x point. X, comma, y, but that's our x, f of x. Our second point on the secant line, this one right here, well, we can call that one x plus change in x. That's going to be the x value. We want to define that in terms of the current x value we are at with our point. And so if I go from our point over to this new one, I am moving some amount on the x-axis, some kind of undefined, indeterminate amount, and we call it change in x. So we have x plus change of x, which means what is our y value at this place? F of x plus change of x. And already the notation seems to be getting out of hand. It's kind of crazy, but just f of your x value, that's your y value. So this is our y point right there. Now thinking about it like this, let's think about the slope of that green secant line. Its slope would be y value minus the other y value divided by x value minus x value. Now, again, a daunting formula with a lot of notation, but it sort of makes sense. It's a y value minus y value divided by the x value minus x value. This is just our slope formula. Now before, we had wanted our x value to get closer and closer to our original x value. And that's where we said the limit as x approaches 0.5. Now what's our goal in this one? Well, we still want this value to move closer, which means we want this x value to move closer and closer to here, which means what happens to that change of x value? It gets smaller and smaller. And in fact, what we want is for our change of x to eventually equal 0. But that would be a problem if we just let change of x equal 0. Because if that happens, I would have f of x plus change of x, which would be 0. So I'd have f of x plus 0 minus f of x. On the bottom, we'd have x minus x, which is 0. So I would have 0 over 0, a problem. And so this is where we come back with our limits. We don't want change of x to equal 0, but we want it to get infinitely close to 0. We want the limit as change of x approaches 0 of our slope equation right here. And on the bottom, those x's do cancel, you can see, and so it's just change of x. And so we have that, and with our function we have right here, we could even plug that in, and limit as change of x approaches 0, f of x plus change of x, so I take my function, and I plug in x plus change of x, and I go minus f of x, which is just my function, divided by change of x. Now you're a little skeptical with this. I'm pretty excited about this formula. I see the light. I see, hey, we just figured out the slope of this equation. But you're looking at it a little skeptical because it's pretty messy. And the change of x, like what is that? We haven't worked with that notation. Well, just a variable. It's a r or an s or a y, whatever you want. But this right here is called the difference quotient. And it is the foundation of the limit definition of the derivative. And all of that is beyond where we're at now. But by introducing this concept of a limit, it allows us to solve this equation, which allows us to find the slope of our function. It allows us to find the slope of something that is not a linear function, something that's curving and changing over time. And that is super powerful. So now I'm going to show one more reason that we have limits. Because what I'm trying to emphasize here is, why do we have the concept of limits? This concept of allowing us to approach something really, really close, but not touch it. And in fact, let me state that clearer. A limit is the idea of getting infinitely close to a number that you can mathematically say you are equal to that number, yet you are not actually that number. And that's a philosophical debate at the foundation of when calculus was founded. Philosophers pitched in about, you can't do that. You can't be at something and not at something. You can't be A and not A. Now it is a mathematically sound idea to use this limit. And so you will see when we start working with limits, it's pretty simple, the first things we start out with. This is a little bit more advanced, but it provides a better reason of why they exist. So with that, let me show one more reason why we have limits. This function right here, y equals x cubed minus 2x squared minus 3x over 2x minus 6, has a hole at x equals 3. Now I emphasized it when I created this graph because I really wanted to show how there's a hole, but you kind of can see if I plug in a 3, I would get 6 minus 6 in the denominator, which equals 0, and you can't divide by 0. And so there's an issue. I cannot find what this function equals at x equals 3. And in fact, it doesn't equal anything because if you plug it in, it's undefined. But you might be interested in figuring out a little more information about it, which is, I know it doesn't equal something, but what value would be here if it could be? What is the value as I get closer and closer to this? What does the y value equal? And now with our previous talk, you might be coming up with the idea of what we can do. Because in order to find out more information about what the function's value would be at x equals 3, what we want to do is figure out the limit as x approaches 3 of that function. Because we can't just plug 3 in, again, that would divide by 0. But what about if I'm at 2.99 or 3.001 or 2.999? As my x value gets closer and closer, we are approaching some y value. And on the graph, you can see it approaches 6. And in fact, if I were to solve this limit, you would get the answer 6. Because that is the y value that we approach as the x value approaches 3. And as you dig into limits more, you will see that limits go from as easy as having a function and plugging it in to find the value. So you can just do 16 plus 12 equals 28, and that is the value of your limit through direct substitution, to a little more complicated, such as this one, where if you plug it in, you get a problem. However, you can work with that and eventually solve the limit using a different technique. And then they get a little more complicated, like the difference quotient we saw in the previous examples. So like with all math problems, there's different levels of difficulties of solving them. But I hope in this video we have seen a little bit of the motivation behind why we have this concept of a limit before we go into actually just solving a lot of them.